Hello, this is the April 6th, 2020 lecture. We're going to start where we kind of left off last day, which is a good place to start. We're going to talk about the chemistry of nitrile groups. So as you're seeing, we're going to start with the hydrolysis of nitriles. Last day we talked about the formation of nitriles using a variety of techniques. In today's reactions, we're going to be changing the nitrile group into something else. In this case, we're hydrolyzing the nitriles to carboxylic acids. There's two ways to do this. There is the acid catalyzed hydrolysis or the hydroxide hydrolysis. On the top, shown in yellow, is the acid catalyzed reaction to form the carboxylic acid directly, and on the bottom, shown in orange, is the reaction with hydroxide and water followed by an acid-water workup. This is required. The acid-water workup, is required because otherwise the carboxylate will be deprotonated and soluble in water, so you need to protonate to precipitate the material and collect it. These two methods both work well, and you decide which method you want to use simply based upon what are the functional groups that are on your structure and therefore might be sensitive to acid and base conditions. If you have something that's sensitive to acid conditions, you would use the hydroxide method to hydrolyze the material. So shown below this is the acid catalyzed mechanism. As I've said in the past, if you have acid, you might as well use it. So in this case, we're going to protonate the nitrogen of the nitrile group. So the lone pair electrons on the nitrogen protonate, shown in green. This forms a protonated nitrile group, which can be resonance stabilized. The electrons in the pi bond here move out to nitrogen. This moves the positive charge to carbon. This is simply a resonance structure. And you can switch interconvert between these. But what protonating the nitrile group does is increases the electrophilicity of the nitrile group itself, specifically because of electronegativity and such, more at the carbon. So now a weak nucleophile can nucleophilically attack, and in this case water, shown in pink, attacks the positive charge on carbon and forms this protonated amide tautomer. What we're going to do is we're going to move the proton from the oxygen over to the nitrogen. This is something that could happen in two steps. I'm showing it as a simple proton transfer within the molecule. Two-step mechanism is also possible, but for the purposes of what we're doing here, I'm just going to transfer over directly. Once we do this, the reason that we want to transfer this proton over is now this positive charge that was located on oxygen originally is now on nitrogen. But what's important about this is this can now be resonance stabilized, and you know how I love resonance as a way of explaining why something can form. So in this particular case, now we have resonance stabilization of our intermediate, and if you look at this and squint your eyes, you say, well, that looks a lot like an amide, and that is going to be the theme of what you're going to see in the reaction of nitriles under these two conditions. We are going to form an amide, and then at that point, it's going to undergo acid or base catalyzed hydrolysis to the carboxylate. At any rate, now the protonated amide is going to be nucleophilically attacked by water, shown in yellow here. This forms a new tetrahedral intermediate, and I've shown a proton transfer in pink. Again, it's a simple intramolecular proton transfer. Again, it could be a two-step mechanism. It doesn't really matter. I'm just showing it as a single step. And then this tetrahedral intermediate is now important because now the nitrogen is positively charged. This makes it a much better leaving group. So now lone pair electrons on oxygen can come in to reform a carbon-oxygen double bond, and NH3 leaves. This forms a protonated carboxylate group. This proton will be lost very quickly. What I've shown in green here is simply the ammonia picking up that proton to form carboxylic acid and ammonium ion. Okay, on the next page, we're going to look at the hydroxide catalyzed mechanism. In the hydroxide catalyzed mechanism, you're going to see that, again, first thing we're going to do, we are under basic conditions. So let's have base react with our material. So we're going to have nucleophilic attack of the hydroxide on the nitrile carbon. This pushes a pair of the electrons that are in a pi bond out to nitrogen. This creates this negatively charged intermediate. Okay, in this particular step, Again, it could be a two-step or one-step process. I've shown the proton transfer being intramolecular, the nitrogen picking it up off of the OH. You could protonate the nitrogen first and then lose the proton off of oxygen. It doesn't matter. I'm showing it in a single step. Here, again, if you squint your eyes and look at this, it looks a little bit like an amide. This is a resonance stabilized species, so the negative charge can reside on either the oxygen or the nitrogen. Gotta love resonance. When this happens, now the nitrogen could be protonated, and you'll see that we've now formed an amide. As I said previously in the acid mechanism, amides are what we're getting to at one point. I may not have mentioned that they rarely stop this reaction at the amide. It's difficult to stop it at this stage because you need fairly strong conditions for the hydrolysis to occur. At any rate, now hydroxide attacks the carbonyl oxygen, creating a tetrahedral intermediate. This tetrahedral intermediate, shown in green here, undergoes breakdown where the carbonyl, or where the oxygen with a negative charge pushes a pair of electrons in to reform a carbonyl group. This loses NH2-, shown in pink, the NH2- picking a proton up off of our carboxylic acid to form carboxylate and ammonia. Again, what we're going to have to do is we're going to have to protonate this material under an acid-water workup to form the carboxylic acid. This is a hydrolysis reaction. We've not changed the oxidation state of our material at all. What we're going to do next is we're going to reduce the nitrile via organometallics. Now we can reduce it with a number of different techniques or species. We could use organometallic like a Grignard reagent. We could also use like lithium aluminum hydride or these sorts of hydride reducing reagents. There is a variety of things that could be used under these conditions. We're going to start with a Grignard reagent. We're going to simply react our nitrile group with the Grignard reagent. It will act, the Grignard reagent will add to the nitrile carbon. You will form a negative charge on the nitrogen. This will form a salt with the magnesium initially, and then under acid-water workup, instead of getting a nitrogen with a hydrogen attached, a doubly bonded nitrogen, with a hydrogen attached, we see that we form the ketone. What happens is this imine species simply hydrolyzes to the ketone. So if we take benzonitrile, react it with methyl magnesium bromide in ether, then we do an acid-water workup, we end up with acetophenone, which is the common name for this particular species. I guess it could also be called 1-phenylethanone as another name for the compound. Of course, this reaction requires that a stoichiometric amount of Grignard be used. Reaction works well, just have to watch your reagent, relative amounts of your reagent. We're next going to reduce our nitrile group with a lithium aluminum hydride. As I'm sure you remember, these reagents are very reactive. I keep talking about them as kind of the hammer. They are very reactive species. So we're going to use lithium aluminum hydride to reduce our nitrile group. What happens in this reaction is the nitrile is going to be reduced all the way down to the amine. So the reagents are lithium aluminum hydride and diethyl ether, acid-water workup once again, and we will end up with, in this case, propylamine. So we use the following our nitrile, propionitrile starting material, and we get our propanamine product. We could also use dibol. As you remember, dibol is a way of adding a stoichiometric amount of hydride. With lithium aluminum hydride, it's very difficult to control the conditions of the reaction or control the stoichiometry. This is such a strong hydride reducing reagent, it just tends to react as far as it can go. Dibol will deliver a stoichiometric amount of hydride, so we can reduce this to a carbon-nitrogen double bond technically. But like we saw with the Grignard reagent, once you work this up under acid-water conditions, that CN double bond breaks down or hydrolyzes to the aldehyde. So we can make aldehydes by this means. Another method of performing this reaction is via hydrogenation. So you can see here we have a nitrile compound. We're going to treat it with hydrogen, and platinum oxide. In this particular case, one could use palladium carbon or Raney nickel. At any rate, one can reduce these to the amine. The thing you need to be careful of here is 1, 2, 3, 4. This is a 5-carbon chain. We sometimes forget about that carbon in the nitrile group, and when we hydrogenate this, we do apparently extend the chain. It's not extended. It's still a 5-carbon chain, but be careful about this. Okay, chapter 21, amines and their derivatives. It's not particularly surprising to think that nitrogen has made its way into biological chemistry and also organic chemistry, since about 4/5 of our atmosphere consists of nitrogen gas. So, in fact, one would expect nitrogen to maybe have a larger role than it does in organic chemistry or biological chemistry, although it has a pretty major role. So shown on the bottom of the page here are some typical amine examples. We have adrenaline on the left. This is something that, when the lion is chasing you, you get a burst of adrenaline, you can run faster than you've ever run before. An interesting molecule, and I've tried to keep a structural theme here of structurally similar molecules. In the center is a molecule that's important to me right now, being spring and such. Benzodrex is a nasal decongestant. You can see that it's not an aromatic ring, it's just a cyclohexane ring here, but it has the effect of being a nasal decongestant. And then right beside it, very structurally similar, is amphetamine. And amphetamine is an antidepressant, and a central nervous system stimulant. Okay, so we can see that while these two molecules have some structural similarity, albeit one has an aromatic ring and one has a cyclohexane, their effects are completely different from one another. Okay, and if we change the structure of the amphetamine a little bit more, and we add a methyl group to the nitrogen, now we create N-methylamphetamine or methamphetamine, and this is actually a potent central nervous system stimulant. The drawback of this material is that it is also quite addictive. So one doesn't see a lot of medicinal use of this material because the patients get addicted to it so quickly and easily. These are just a few examples of some of the biologically active amines, and they are important biologically. Nomenclature of these compounds is quite simple. We drop the E of the alkane name and we add amine, so an alkane becomes an alkanamine. As with alcohols and molecules of this type, you only count the carbon chain. You do not count the nitrogen or heteroatom, as we saw with alcohols. So this becomes methanamine. Quite simple. Here we have a 3-carbon chain, so a propane parent name. As with alcohols, the nitrogen is automatically given position 1, or the end closest to where nitrogen exists is position 1. So this becomes 2-methyl propanamine, 1-propanamine. Underneath this is a more fun example. It's more fun because we have a double bond that has some stereochemistry. We also have a chiral center in our molecule, so we've got to incorporate all of these aspects into our name. On the name of this compound is R-trans 3-pentene 2-amine. Now this illustrates the example of illustrates the example of when we had alcohols that had double bonds and such. Since the double bond and the alcohol are expressed in the parent name, we start moving numbers around a little bit. So 3-pentene indicates the position of the double bond, the 2-amine, 2 indicating where the NH2 in this case is situated on the molecule. Of course, there's only one stereocenter, so one does not need to put a 2R in this particular case. Now, if we have amines that have 2 amino groups on them, they become simply diamine compounds. So some examples of diamine compounds here. At the top, 1,4-butadiamine. That's simply how it's named. This has a common name, and the common name is putrescine. Hopefully that will give you a sense of how bad this material smells. The one beside it, 1,5-pentane diamine, has a common name of cadaverine. Obviously, these materials are formed during the decomposition of biological, probably animal biological materials, and they were first isolated from those forms, and hence the wonderful common names that they were given. I've worked with some of these diamines, and the name does not do justice to how bad they really smell. Underneath this is just one more example, benzene amine. This is what this should be named according to the system. Again, the use of common names is very highly used in organic chemistry, so the common name for this is aniline. Now, what if we have substituents on nitrogen? These groups are handled as simply an N substituent, just like amides. So we don't add it to the chain length. All we simply do is we're putting a nitrogen on the, we're putting an alkyl group on the nitrogen. Probably won't be in the online notes, but I'm adding an H to the nitrogen. Sorry about that. So this becomes an N-methyl substituent. So the molecule is ethanamine, 2-carbon chain with a nitrogen attached, ethanamine, and the methyl group is an N-methyl ethanamine. Here we have a parent chain that is propanamine. Since the nitrogen is in the 1 position, you don't have to necessarily put the number in front of the molecule, and in this case it's got 2 methyl groups on the nitrogen, so this becomes NN-dimethyl propanamine. Remember, just like when we have 2 substituents on the same carbon, you have to put that number twice. Same thing here. This is NN-dimethyl propanamine. Now, there are situations where nitrogen is a substituent. So in those cases, the nitrogen group is named as an amino group. So, for example, here we have 1, 2, 3, we have propanoic acid is the parent name. Carboxylic acids are higher priority than nitrogen groups. So this becomes propanoic acid is the parent name. It has an amino group on the 2 position, 2-amino, 3-phenyl propanoic acid. The example underneath, alcohols are higher priority than amines, so we have a molecule, it's called 2-amino cyclohexanol. I put a little separation in here. These are all one-word molecules. I apologize for having that little separation. Okay, last page of notes for today's lecture. Yay, but you'll see there's a lot of writing on here. We're going to be talking about the structure of amines. Now, nitrogen is going to be sp3 hybridized, and it's therefore going to have a tetrahedral orientation or shape. That's not a surprise to anyone, hopefully. But what's a little bit different about it is because one set of groups, or one group on it, is a set of lone pair electrons that are invisible to us, the shape of an amine is trigonal pyramidal, because we can't see those lone pair electrons. But the interesting thing to think about here is that because of the tetrahedral shape, one might expect that these can be chiral. Okay? And in fact, this is not observed. What is observed is the fact that nitrogen can flip back and forth very easily. So it's shown down here, you can see that I have 4 different groups on my nitrogen. Technically it should be chiral, but what we see is at room temperature, these things flip back and forth. And if you think about it, it's not surprising, because if you think about the transition state for this, if we convert this from sp3 to sp2 hybridization, now these electrons are in either shape, and when it goes back to sp3 hybridization, it can go having that lone pair electron in either orientation. So what happens is this interconversion occurs very quickly, and this interconversion occurs, the energy required is about 5 to 7 kilocalories per mole. So at room temperature, there's lots of energy available for this reaction to occur. So interconversion occurs very easily. I skipped over it, so I'm just going to go back to it quickly. The NC bond here is 1.47 angstroms. The bond angle between the H and the CH3 is 112.9. You can see that the larger group kind of pushes this a little further away, and the two hydrogens are a little closer together at 105.9 degrees with the NH bond about 1.01 angstroms. That pretty much wraps up today's lecture about amines. I still think it's cool that amines can flip back and forth. Everybody have a great day. I will see you next lecture. Thank you.